My name is indeed Antoine, and today I'm going to tell you about our system, DSig, short for data center signatures, and how DSig broke the barrier of signatures in the data center. To start this presentation, let's have a short recap on what are signatures, how they work, and why you would use them, just in case so that we have everyone on board. So signatures are essentially certificates of authenticity. That is, if you get a message with my signature on it, well, then you pretty much know that I'm the emitter of this message. Importantly, signatures are transferable. That's a key property, which means that if you were able to check that I was the emitter of this message, then you can just forward the signature to someone else, and this person will also be convinced. And that's a key difference with other authentication techniques like MAX, which do not provide this feature. Now, as to how signatures work, well, they do rely on asymmetrical cryptography, which means that to sign messages, processes use a private key that they are the only one to know, and to verify signatures, processes use a public key that is made available to everyone. Now, why would you use signatures? Well, very easy, because they enable a ton of super powerful protocols. Let me just give you a couple of examples. So some of these protocols are like crypto-secure audits. For instance, for many applications, it's very important that they report to authorities, to regulators at the end of the day, everything that happened, so that, you know, if the regulator can look in what was executed through the day and try to see if there's anything fishy. So if you can make those audits crypto-secure, that's very nice. So all you would have to do is to ask the clients of those applications to sign their requests, and then it becomes very hard for those services to fake their logs, essentially. And that's something that you would want, for instance, from trading applications, just to make sure that nothing fishy happens. Another use case for signatures are to build Byzantine fault-tolerant protocols. Those are protocols that essentially allow you to tolerate faults that go beyond crashes. So for instance, if parts of your system got compromised, well, maybe you could just keep on going despite these hacks thanks to BFT protocols. So yeah, signatures are very powerful. What's the deal with signatures in the data centers? Well, first of all, you have to realize that data centers today, just like the rest of the internet, they host a lot of mutually distrustful users. The reason for that is that data centers offer very high performance, and notably the latency within the data center is getting to the microsecond scale. That's kind of a requirement for many applications, such as high-frequency trading. And so because of that, yeah, we have distrustful users within the same data center. Which means that if you were to be given microsecond-scale signatures, then you would be able to have crypto-secure auditing for instance, high-frequency trading, or you could also have microsecond-scale Byzantine fault tolerance. But we're not quite there yet, because if you look at the state-of-the-art, which is EDDSA, it doesn't quite provide the performance that you need. Here we have, on the right, 3 different applications. The first one is a key-value store that we augmented to provide those crypto-secure audits. The second one is a broadcast primitive that is BFT. And the third one is a BFT replication primitive. Well, what you see is that for all those applications, basically signatures, they represent 90%, or let's say 80+% of their latency. That's just too much. What we propose, thanks to DSig, is to drastically reduce this overhead so that you can finally have these protocols at the microsecond scale. And this is what this talk is going to be about, how to reduce the overhead of signatures by 80+%. And a cool thing is that we do so without weakening the signatures. That is, if you use DSig, you're still getting the 128 bits of security that, for instance, EDDSA would provide. Okay, so how do we get there? What are the observations and the key insights? The first observation is that traditional signatures, such as EDDSA or even worse, RSA, are super slow. But they're very practical because using them, you can virtually sign infinitely many messages. Now, on the other hand, there is another kind of signatures that are like less well-known. Those are one-time signatures, and those are blazing fast. The reason for that is that they can sign messages using only a couple of hashes, and the same goes for the verification of the signatures. However, as their name suggests, there's a big drawback, that is that those keys can only be used to sign one message, because every time you sign something with those schemes, you're revealing parts of the secrets, so if you were to sign multiple things, that would become unsafe. So as you can imagine, one-time signatures are not very practical because they are kind of costly to set up. Every time you want to send a message, you have to generate a new key that's expensive. Not only do you have to generate it, but you also have to distribute it to the verifiers in a safe manner. That is a bit tricky. So that doesn't quite give us the microsecond scale performance in a practical fashion as we're expected. But maybe there are a couple of insights that we could leverage to get there. The first one is that when you have an application in data center that requires signatures, well, you pretty much know who the verifiers of this signature are going to be at the moment you produce the signature. Like, let's say that you have this trading application. Well, when I need to buy order, well, what I know is that the person who does the order matching of the requests, this person needs to verify the signature very fast because it's on the critical path of the operation. But, and I know this person in advance, but for all the others, for instance, for the person who is going to audit this application at the end of the day, it doesn't matter if this thing is a tad slower. So what we propose to do is to extend the interface of traditional signatures so that in addition to saying, look, I would like to sign this message using this secret key, you say, I would like to sign this message using this secret key. And by the way, here are the people that are going to verify this thing on their critical path. So it's very important for them for the thing to be fast. And that allows us to adopt a fast, slow path design. In the fast path, you will have been able to set up the one-time signature scheme ahead of time so that on the critical path, you really have very little to do. Whereas on the slow path, you won't have been able to set up this OTS ahead of time. And so you're going to have just enough information embedded inside the signature so that this OTS can be set up on the critical path. To be more precise, this information that you need, it's what is the public key that this OTS is using, and also you need to have you need to authentify this this public key using a traditional signature. So this is what you get at the end of the day. You get a hybrid signature that is made of 3 components. The first one is a one-time signature that is going to be checked on the fast path, and on the fast path, that's pretty much the only thing that you will have to check. Whereas you have these 2 more components, the OTS public key and an DSig signature on this public key that are going to be used on the slow path only. Okay, so given these key insights, how does DSig actually work? Let's get to see an overview. Well, let's imagine that you have an application that has 2 different processes. The one on the left is a process that is interested in signing stuff, in signing messages, while the one on the right is interested in verifying those messages. Well, those processes are going to use the DSig library, which is going to provide the following interface, just sign on one side and verify on the other. Very importantly, this library is split in 2 planes. There is a foreground plane that is responsible for all the operations that are very, that have to be very low latency. It's everything that is going to happen on the critical path. And everything that is expensive to compute, we're going to move it to the background plane so that it doesn't impact the foreground one. So one element that you will find in the background plane of the signer, for instance, is the generation of the OTS keepers. As I told you before, every time you want to sign something, you will need a new OTS keeper, so you keep on generating them in the background. Then, once those things are generated, you need to sign them so that you are able to distribute them to the verifiers. Of course, the throughput of EDDSA is not that amazing, so if you were to sign keepers individually, the throughput would be kind of bad. So what you're doing is that instead you're assigning batches of OTS keepers, and once that's done, the keeper is ready to be used by the foreground plane, so you just queue it for it to be later consumed by the foreground. Then, in the meantime, those signed public keys are forwarded to the verifier, so that in the background, the verifier can check the EDDSA components the EDDSA certificate on this public key, and ahead of time be like, oh, okay, I know this public key, it indeed belongs to the signer, so if I see it later on the critical path, well, I won't have to check it again, because, like I cached the fact that this was a correct public key. Then, when you're on the critical path, the signer is going to call the sign function, and it's going to provide a hint. This hint is going to be the list of verifiers that will need to check the signature on their critical path. So those are verifiers to whom the public key was forwarded ahead of time. All the foreground plane of DSig has to do is to fetch a public key that was pre-computed from the queue there and called the very cheap OTS sign function. Again, it's essentially like a microsecond to do so. Then the signer gets a hybrid signature that it can forward to the verifier. On the verifier side, the guy called verify function. This verify function leverages the cache, so it knows that the EDDSI component of the hybrid signature was already verified, and so it just has to call the cheap OTS verify function. So that's it. That's the overview. That's how DSig works. Now there's a key component that I didn't tell you about so far, which is how to pick the right OTS. Because I told you that one-time signature schemes were fast, but in fact, there are like tons of them. There are a lot of options. There are many schemes. All of these schemes, they have like very large parameter spaces, and there are like a lot of trade-offs to consider. Maybe the most important trade-off is the one between compute and bandwidth. Usually, when we talk about signatures, we don't really care about bandwidth because we are used to signatures that are like very small. But when you are using OTSs, that's not the case because the signatures tend to be larger, plus there is stuff that you have to send in the background. So you have to consider the bandwidth. If we were to plot EDDSA on this graph, and it's not an OTS, it's just for reference, it would be there. It's like it demands a lot of compute, and the bandwidth requirement is very, very small. OTSs, usually they are used for machines that have very low compute abilities, but that don't have a lot of bandwidth either, so people try to stay in the middle. In our case, thanks to our specific setting, what we're doing is that we're focusing on OTS schemes that require very, very, very little compute, despite the fact that we have server machines that are very powerful for the thing to be super fast. But we don't really care about the bandwidth. I mean, we can afford like 3 times the bandwidth for traditional OTS scheme if that allows us to get lower latency. That's because data centers offer much more abundant bandwidth than wide area networks. Now, let's jump to the evaluation of DSig. We ran a lot of benchmarks, micro benchmarks on the latency of DSig, its throughput, its scalability, as well as many macro benchmarks on how it integrates with end applications, what is the latency that it brings to them, what is their throughput. We have also fine-tuning benchmarks on how to pick the OTSs that are going to yield the best performance, as well as their resource consumptions, and also like how to pick the right size for the EDDSA batch size, for the EDDSA batches that I was telling you about before. Overall, because we have time constraints, I'm going to focus on the latency of DSig, its throughput, and the latency it brings to end applications. So about our evaluation setup, well, it's a very standard one. We're just using a regular data center, server machines. We're using traditional Linux. More importantly, for the networking, we're using RDMA-enabled NICs, and that's what allows us to go microsecond scale. And if you have a traditional adapter, I guess you will have a harder time getting there. And we match it with a 100 Gbps InfiniBand switch so that, the network goes fast. So if we have a look at the latency, here we have plotted the latency to sign a message, transmit the message plus its signature, and verify the signature on another machine. So there's like it's a one-way communication. And so we have plotted the latency for EDDSA, which is the state of the art, DSig, our protocol, and DSig when you fail to provide it with a good hint. And what you see is that DSig has 27x faster signing time and 7x faster verification. And what is kind of cool is that even when you fail to provide good hints to DSig, well, overall the thing is still faster. The reason for that is that despite the fact that the verification is a bit longer, well, signing is still stupidly cheap, if you will. So overall, we are faster, even in the slow path. Now, what about the throughput? Well, what you see here is the throughput of DSig versus the throughput of EDDSA, and you can see that DSig achieves 2.4x higher throughput than EDDSA at a much lower latency. Now, what about integrating DSig with end applications? Here we have 5 different applications. The first one is HERD, a key value store that is optimized for the microsecond scale that we augmented with those crypto secure audits I was telling you about before. The second one is Redis. It's a key value store that you will more likely find in web applications that we also augmented with audits, crypto-secure audits. Liquibook is an order matching engine that we also provided with audits. CTB is a broadcast primitive that is BFT, and UBFT is a replication engine that is BFT. And what you can see is that DSig helps reducing the end-to-end latency of these applications from like 69 to 83%. So that's a drastic decrease in their end-to-end latency. So to conclude, DSig enables microsecond-scale signatures in data centers, and as we have seen, that has many applications, and we also hope that this will bring new secure applications to the data center. DSig is able to sign in less than a microsecond, to verify in less than 5, and the signature that you produce can be transmitted in less than 2 micros. The signing throughput of DSig versus the state-of-the-art is 2.5x higher, the verification throughput 7x higher. DSig is open source, available on this GitHub repo. Of course, check our paper if you have some more questions, and otherwise I'm ready to take the questions that you are going to have live. Thank you very much.